This is the second video in this series on pulmonary function tests, and the topic is spirometry. The objectives of this video are to understand the meaning of FEV1, FVC, the FEV1 to FVC ratio, and the flow volume loop. To be able to use these values during diagnostic evaluations, and to understand how FEV1 can be used to grade severity of disease. So what is spirometry, and how is it performed? It's essentially a technique used to measure airflow and some lung volumes. Spirometry has been around a long time. Here's a representation of the basic principle behind the original method. A patient would breathe in and out through a tube that was continuous with an upside-down, partially submerged chamber. The height of the chamber was related to how much air had been exhaled or inhaled, and this volume of air could be plotted as a function of time, thus providing rudimentary information about airflow. Of course, modern spirometers look quite different, with circuits replacing the pulleys and counterweights. The actual procedure to measure spirometry is very simple. The patient places his or her mouth around the mouthpiece of the device, inhales maximally, and then exhales as fast as possible, and continues to exhale for at least 6 seconds. The maneuver is repeated at least 3 times, and the highest lung volumes and highest airflows are recorded, even if those two values are from different attempts. Let's take a closer look at the measures of airflow and volume. This graph probably looks familiar from the last video. For right now, the only subdivision of the volume that we'll focus on is the vital capacity. And actually, when the vital capacity is measured within the context of standard spirometry, that is, within the context of the patient exhaling as quickly as possible, it is known more specifically as the forced vital capacity, or FVC. If we then look at just the volume of air exhaled during the first second of that forced exhalation, this is called the forced expiratory volume in 1 second, or FEV1. The FVC, FEV1, and the ratio of FEV1 to FVC are the 3 most important values in PFT interpretation, as we'll see in a few minutes. Let's look at the FVC and FEV1 from a slightly different perspective. This graph of exhaled volume as a function of time will be more typical of the graph actually produced by the modern digital spirometer. Once again, the patient starts with a full maximal inspiration and then exhales out as quickly as possible. The volume exhaled within that first second is the FEV1, and the maximum exhaled volume, typically achieved by 6 seconds or so, is the forced vital capacity, or FVC. An additional parameter can easily be measured from this graphic form. You may know that airflow is a measure of the change in volume over the change in time. Therefore, the maximum slope of this curve is equal to the peak expiratory flow rate, sometimes abbreviated PEFR. Let me compare that graph to another one, something specifically called the flow volume loop. The flow volume loop is a graph of airflow as a function of volume. During expiration, there's an initial quick peak airflow and then a gradual reduction in flow until it reaches 0. The inspiratory half of the flow volume loop is much more symmetric. As I just mentioned, the maximum slope of the graph on the left is the peak expiratory flow rate, which is the same flow at the maximum point on the graph on the right. The volume present within the lungs at the transition from maximum inspiration to expiration is equal to the total lung capacity. The volume present within the lungs at the transition from maximum expiration to inspiration is the residual volume. As you may have already deduced, using only spirometry, it is impossible to know the starting point of the flow volume loop's x-axis. That is, it is impossible to know the value of the residual volume or the total lung volume. However, the difference between them is the forced vital capacity. Although at first glance it would seem that the flow volume loop does not provide any new information, however, the shape of the curve itself, irrespective of the peak flow in FVC, can provide important insight into a variety of lung disease, most prominently the different types of airway obstruction. So in summary, the major values measured by spirometry are the FEV1, the FVC, the FEV1 to FVC ratio, and the flow volume loop. There are also some minor or less important values measured. We just saw the peak expiratory flow rate. There is the FEF 25 to 75, which is the average flow from the time 25% of the FVC has been exhaled to the time 75% has been exhaled. This value has historically been used to detect obstruction in the small airways. However, some experts argue that the validity of this association is overstated. There is the maximal voluntary ventilation, or MVV. The MVV is the maximum amount of air that can be inhaled and exhaled within 1 minute. Finally, after spirometry has been performed, the patient can be given a bronchodilator, and spirometry then repeated to assess for any response. I'll now discuss how the information provided by spirometry can help with diagnosis. For now, we'll compare the values of the FEV1, FVC, and the FEV1 to FVC ratio for both obstructive and restrictive lung disease. In obstructive lung disease, for example, COPD, the FEV1 can be normal in very mild obstruction, but it is almost always decreased. This makes intuitive sense. If the airways are constricted or obstructed, it will take longer to push air through them. The FVC will be normal in mild or moderate obstruction. However, for a variety of reasons related to lung mechanics, the FVC will decrease with more severe degrees of obstruction. As a very consistent rule, in obstructive lung disease, the FEV1 will decrease to a greater degree than the FVC. Therefore, the ratio of the two will decrease below the normal value of 70%. This ratio is rarely referred to as the Tiffonot index. In restrictive lung disease, the FEV1 is either normal or decreased, and the FVC is decreased. As the FVC is usually decreased to a similar or greater degree than the FEV1, the ratio of the two is either normal or increased. Use of the FEV1 to FVC ratio to distinguish obstructive from restrictive lung disease is literally the single most important thing to remember about interpreting PFTs. Let me redisplay this information in a diagnostic flowchart. When interpreting PFTs, the first step is always to assess the FEV1 to FVC ratio. If it's low, assess the FVC. If the FVC is normal, the patient has some form of obstructive lung disease. If the FVC is low, the patient may either have severe obstructive lung disease alone or a mix of obstruction and restriction. Returning to the ratio at the top, if it's normal or elevated, assessing the FVC is still the next step. If the FVC is low, the patient may have restrictive lung disease. If it's normal or high, the patient has normal lung mechanics. At this point, I'll address a question that some viewers may already have. Where is pulmonary vascular disease in this algorithm? In the last video, I mentioned that it was one of the 3 major categories of lung disease, at least lung disease from the perspective of PFTs, but I haven't mentioned it at all here in this video. That's because pure pulmonary vascular disease is actually characterized by normal lung mechanics. It cannot be distinguished from completely normal lungs using spirometry alone. Obviously, this chart is incomplete. On the leftmost outcome, we have an obstruction or mixed disorder. Then further across, there is a, quote, possible restriction. And last, as I just said, we can't use spirometry to distinguish pulmonary vascular disease from normal. In the next 2 videos, I'll be adding to this algorithm information learned about the lung volumes and DLCO in order to remove the majority of this uncertainty. What about the variations of the flow volume loop? Aside from the normal, there are 6 typical patterns of which you should be familiar. Here we have a graph of volume versus time on top, and the flow versus time on the bottom for a patient with mild obstruction. In the top graph, you can see that FVC is preserved. However, it takes longer for the patient to get there, which is represented by a late plateau of the volume. In the flow volume loop, the peak expiratory flow rate may be mildly reduced, but more significantly, there is deformation in the middle of the expiratory limb of the loop, usually referred to as a coving. This qualitative finding is analogous to the quantitative finding of a reduced FEF 25 to 75%. In the next situation, severe obstruction, a reduction in the FVC is visible in both curves. In addition, in the flow volume loop, the peak flow is severely reduced and coving may be even more pronounced. In restriction, since airflow is normal, the plateau in the upper graph is achieved quickly. However, FVC is reduced. You'll notice that the flow volume loop looks like a normal loop that has been shrunken in all directions with no coving present. In addition to those three patterns, there are three classic patterns of upper airway obstruction, which would not be included in the general category of obstructive lung disease. The first is variable extrathoracic airway obstruction. In this condition, during expiration, the intratracheal pressure exceeds atmospheric pressure, which helps to keep open the airway despite obstruction. However, during inspiration, the intratracheal pressure is below atmospheric pressure, so the extrathoracic airway has a tendency to collapse. This effect exists even in the absence of an obstruction, but the additional narrowing only becomes flow limiting in the presence of pre-existing obstruction. As you can see in the flow volume loop, the expiratory limb is normal, while the inspiratory limb is blunted. In a variable intrathoracic obstruction, during forced expiration, the intrapleural pressure is higher than intratracheal pressure, so the intrathoracic upper airway collapses during that phase of respiration, limiting airflow. Inspiration is normal. And as you might imagine, if airway obstruction was fixed throughout the respiratory cycle, maximum airflow would be blunted during both expiration and inspiration. Here are some etiologies of the various types of upper airway obstruction. Vocal cord paralysis as a cause of variable extrathoracic obstruction is probably the most classic example. In addition to diagnosis, spirometry has a few other roles. For example, in COPD, the severity of disease can be staged based on the FEV1. The Global Initiative for Chronic Obstructive Lung Disease classifies COPD severity as follows. Stage 1 means that the FEV1 is greater than or equal to 80%, that is, it's normal. Stage 2 means the FEV1 falls between 50 and 80%. In stage 3, it's between 30 and 50%. And finally, in stage 4, it's below 30%. Despite this staging system's use in clinical practice, there is actually only a weak correlation between FEV1 and quality of life. Consider the following graph in which a score of quality of life is plotted against FEV1. The higher the score on the scale, actually the worse the quality is. The individual dots each represent a person, and each color band represents a different COPD stage according to the GOLD system. Although there is a statistically significant correlation when the population is looked at as a whole, there is little predictive power for an individual person. In my last minute, I'll mention the assessment of how airflow responds to bronchodilators. If I bring back the PFT report from the last video, you can see that this column is for pre-bronchodilator spirometry results, and this one is for post-bronchodilator. Among patients with obstructive lung disease, a greater than 12 to 15% increase in FEV1 after administration of a bronchodilator is considered significant. However, a lack of such an increase should not preclude a trial of long-acting bronchodilators, as some patients will still have clinical benefit despite the fact that they lack an obvious benefit on spirometry. That concludes the second video on spirometry. The next video will discuss measurement and significance of the lung volumes.